Welcome to this lecture on mathematical induction. Induction is a very important proof technique, but it's just an inference rule, and you can use that inference rule to prove theorems that state that all members of an infinite set S have a certain property P. So logically speaking, the theorems for which you can use mathematical induction have this form. For all x in S, P of x is true. So S is the infinite set in question, X ranges over all the elements of S, and P is the property or the predicate that the theorem states is true of all the elements in S. Now, an extra condition for applying mathematical induction on a set S is that the elements of the set S can be ordered. So it should be possible to refer to the first element in S, the second element in S, the third element in S, and so on and so forth. Now, typically, our proofs by induction are going to refer to the sets N or Z+. Remember that N is the set of non-negative integers starting at 0, 1, 2, and up, whereas Z+ is the set of positive integers starting at 1, 2, 3, and up. Let's say you're trying to prove a theorem of this form, where P is a property of the positive integers. Then you could use mathematical induction, which is an inference rule, and here is its definition. This rule has two premises. The first premise is P of 1. Notice 1 is the first element of Z+. The second premise is P of k implies P of k plus 1, where k is an arbitrary element of Z+. If these two premises are true, then mathematical induction allows you to infer the following conclusion. Namely, for all n belonging to Z+, P of n is true. So that is the definition of the inference rule. Now, if you want to write a proof by mathematical induction, you will have to write two subproofs. The first subproof is going to establish the first premise, namely this one, and this is called the basis of the induction. So the basis step is to prove that P of 1 is true. The second subproof is going to establish the second premise of the induction inference rule, and that is called the inductive step. So that step consists in proving that P of k implies P of k plus 1 for an arbitrary k in Z+. Now, two comments here. Notice this inference rule has a lot in common with recursion. Notice here the form of this conditional is that if you know that k has the property p, then you can infer that the next integer k plus 1 also has the property p. And notice you have a base case here that allows you to get started by establishing that the first integer 1 also has that property. Now, second observation is how are we going to prove that second premise here, this conditional? Well, we're going to do a direct proof, which means we're going to assume that P of k is true for an arbitrary k, and from that alone we're going to have to infer that P of k plus 1 is true. So since we're going to do a direct proof of this, this is going to be called a hypothesis of the conditional. We're going to assume it's true. And this hypothesis is called the inductive hypothesis, since we use it in the inductive step. And of course, it's needed for the direct proof of the second premise. So let me conclude this first segment with a brief discussion of the intuition for why this inference rule makes sense. Why does this conclusion logically follow from these two premises? How could you infer a property P for an infinite set of elements using only two logical true propositions? Well, let's see how this works. So let's assume that these two premises are true. So P of 1 must be true. Let's start with that. And the second premise is also true. Now here's the key. This conditional is true for an arbitrary k, which means it's true for every integer in z plus. Therefore, we can replace this k with any positive integer. Let's choose 1. So from this premise only, we can infer that P of 1 implies P of 2. And now we can use modus ponens with these two premises to infer that P2 must therefore be true. Wait, now we have that P2 is true. So again, we can use the second premise here, replacing k with 2 to infer that P of 2 implies P of 3. And now again, we can apply modus ponens to infer P of 3. And you can see that it's enough to know that P of 1 is true and that P of k implies P of k plus 1 for all elements k in z plus to infer that we're going to be able to conclude that P of n is true for every single positive integer. So that is the intuition for why this inference rule is logically valid.